All right, my name's Mark Wiebe. I'm with ThinkBox Software, and I'm going to talk a little bit about point cloud processing. We've got an application we're building called Sequoia, which we've been developing some algorithms and data structures, a file format for. And so I'm here to basically give a little bit of a peek under the hood as to what it takes to write a scalable point cloud kind of system. So to start, I'm going to give a little bit of a run through of what are point clouds and how do they work? What do you do with them somewhat? So a point cloud is basically just in a coordinates system of some kind, a whole bunch of points. You typically have data attached to it, so you can think of it like if you have a table, it's just like X, Y, Z coordinates followed by other data. And what's important in a point cloud is the spatial structure of it, like what it represents something in space. So typically we're dealing with 3D space, and you see it in medical imaging where you can represent volumes as like point clouds, like the number of points can represent density or something along those lines. The most common case is surfaces. So you do LiDAR scanning or photogrammetric reconstructions of surfaces. That's lots of samples of the surfaces of some model. But you can also do curves like hair, or points, like if you want to represent the stars in a system you might be simulating or something. These are all point clouds. And a closely related thing is particle systems, which is a little bit more what I've personally dealt with. And that's, you take a point cloud and you attach some kind of programmable dynamic system to it. Basically, your points might have velocities that depend on neighboring points or some system that's like makes them swirl around. So it's very common in visual effects and in games. These are a couple of screenshots from products that we've created, or from movies that use some products that we created for dealing with large volumes of particles. So that's one of the things is our core strengths is particle systems. But we've got a bunch of software. Highlight Krakatoa, renders large volumes of particles. Frost, meshes, produces watertight meshes, processes very fast. And Stoke is a highly programmable system that's also artist-friendly and lets you remix particle systems so you can kind of replay the same dynamics but on a different, like say more points, or you can then mix it with 3D fields and apply like Eulerian constraints to like manipulate your velocities, make them divergence free, things like that. Kind of like a toolkit of some fluid simulation primitives that kind of let you flexibly tweak things. So our tools are very good at these particle systems, and people started using them on their point clouds in industries outside of what we were normally selling to. So that's where we got the idea to create Sequoia. And I'm gonna like show some of the details of like the foundational building blocks of such a point cloud system. So there's also quite a bit of open source code that deals with point clouds. So this screenshot from Point Cloud Libraries site kind of gives a nice overview of what kind of things you might want to do with point clouds. So you might do a LiDAR scan and get a whole bunch of points. Then you might want to do some kind of filtering, get rid of noise, whatever, segment into different classes, put it into surfaces. This is a very typical workflow. LAS is a very common file format you run into when dealing with point clouds. And there's a library that helps you manipulate them. And it has Python bindings, so you can do some basic things just from Python in this way. It is a little bit tricky to install, and it doesn't, say, integrate tightly as far as I could see with NumPy and some of that. So there is perhaps some things to be desired for it, but it's it's a format you can download a lot of open data that's in this format. There's a library called octree, which is being developed. It's a JavaScript library, but it actually gives you like embeddable web point cloud viewers. So this is an example. It's basically fully interactive in your browser. You can like fiddle around. There's some parameters to tweak things and whatever. Yeah, that's kind of some of the tools that are out there, the free libraries available. Point Cloud Library in particular has some things that are very similar to what I'll be talking about. They have an octree, can deal with large data sets. I'm going to talk about it in a particular way, which I think is really good. First, some background on spatial data structures. If you want to do something sophisticated with a point cloud, you kind of need to put it in a spatial data structure first. And what that's typically going to let you do is ask for, given a point in space, what are the nearest end particles? Or given a ball of some radius, what are all the points within that ball? So some common ones are the octree. Now in an octree, you start with a cube, you divide the cube into 8 subcubes, then you maybe pick some of those and you keep subdividing. Very simple. It's a tree, pretty easy to work with. Another one is a KD tree. So in a KD tree, you start with a box. It doesn't need to be a cube. The sides don't need to be the same. You pick an axis, you split it into 2 half spaces, and then you recursively split those. You pick an axis for those. So in this example, it's alternating between like X, Y, and Z. In the kinds of KD trees I've developed, it's actually advantageous to pick the axis per splitting point based on what the data actually looks like. Another one is bounding volume hierarchy. So in that, you basically find nearby or adjacent objects, you group them together, and then you basically make some kind of tree, maybe a binary tree or multi-way tree. So each of these have different characteristics. So if I go back, like octree is very simple. It's adaptive to the data, can be adaptive to the data in terms of like, okay, there's more points here, let's split more. But which boxes, which cubes you're going to get is predetermined from your root cube. KD tree kind of improves on that a little bit in the sense that now you can choose your splitting planes based on where the data is, and that can get you faster lookups. Maybe you don't have to search as far down the tree, you can skip over things quicker. But it also means if you're like want to modify your points in some way, well now rebuilding the tree is a bigger, more complicated option and operation, and maybe you have to look at your points more when building the KD tree. And the bounding volume hierarchy is actually really good if you have like well-defined things that are moving, like animating. So in like a video game setting, this is the kind of thing you might want for collision detection of animated models that are going around and hitting each other possibly. But it's also very freeform, and like maintaining spatial structure isn't necessarily, like on just fully freeform data, is not quite as well defined as the other ones. So we're using an octree for Sequoia, and it's based on something called floating point Morton order. And this works out really well for scalability, for out-of-core behavior. And so we'll see a little bit why. Something very related is the fast multipole method. And so Lorena Barba gave the keynote this morning. A project she was involved in called ExaFMM is exploring, or it's a library that lets you compute the fast multipole method on like multi-threaded code or on the GPU. And it's kind of pushing the idea of fast multipole method is the kind of algorithm you need if you're going to exascales. You're like, because it's a big O of n algorithm for computing the n-body problem solution. And their code, if you go peek inside and look at the comments and see what they're doing, they're using an octree and they're using Morton order for dealing with the spatial structure of the points. In this case, maybe it's like stars or something if the thing you're solving for is actually like gravity or something. So Morton order, also called Z order, because of how if you pick your axis a certain way, it looks like a Z. It's basically a way to order integer coordinates that has some really nice spatial behaviors. And in particular, it tends to make points that are close together in space, in 2D space in this case, be close together in your 1D linearized version of your points. So I'll kind of walk you through a few steps to understand like what it does, how it's built up. And I'll do that by starting with Morton order in one dimension. And it's not really Morton order because it's like kind of trivial, but it's based on the binary representation of the numbers. So I've broken out 5 and 7. And so 5 is 0, 1, 0, 1. And you can see it going down this diagram. And 7 is 0, 1, 1, 1 going down the diagram. And basically, you look from the most significant bit down to the least significant bit. And at each point, you're splitting your entire space of numbers in two. So we look at the most significant bit. It's the same, so both numbers are in the left half of your number line. And then the next bit is 1 in both cases, so we're in the right half of this subnumber line. We cut our space in half, and then we do it again, and now we see we're a different bit. 5 has a 0, 7 has a 1. And that's the bit that determines the order. Now we've ordered 5 is before 7 because we saw that bit. It's kind of trivial. All we've done is reconstructed integer ordering, but this idea of like looking at the bits in order, it's creating a spatial structure on our numbers. And in fact, that's exactly what Morton order in 2D is doing and Morton order in 3D by analogy. I'm just going to go through 2D in the same way. And so the only difference between the 1D example is now we're going to alternate coordinates as we go. So we start with the x coordinate. And so I've picked two coordinates. This is 5, 4 and 4, 5. And I've gone down to 3-bit numbers. So the first one is 1s, and so it's on the rightmost side. And I'm going to copy those bits here. And let's go to the next one. So we go to the y-axis. Once again, there are 1s here. So it's the same, but we're now looking vertically, and we pick the 1 side. Switch back and go to the next bit, 0s. So see, now we're in this we've like descended one level. We're inside this box, and we picked the 0 side of that. So once again, we're looking for that first bit where there's a difference. We haven't run into it. Switch axes, and we're kind of at the 0 side of that. And now the first place we see a difference is in the x coordinate in the third bit. And that is actually what determined the ordering. So because it was a 0 in 4, 5, this one comes first, and then the 1, 5, 4 comes second. One thing we get out of this is these Morton indices. And you'll notice the way I wrote them out, those are now just binary numbers. You compare them like normal integers, and you get this ordering naturally. So one way to do this is just to take your coordinates, interleave the bits, and now you have an index that defines the ordering. And that's kind of a nice way to think about it. But the other way is the first bit that differed in this index, or the first, like the most significant bit across the two coordinates, kind of breaking the tie towards like the earlier coordinates, is another way of thinking of how we came up with this ordering. And there's a very close relationship between what we just did and octrees. And you kind of saw it in the diagram, because it's like we have the outer box, and it's kind of split into 4 subsquares. And basically we keep descending the squares. So let's do this again, but from that perspective. So instead of grouping the bits as like the coordinates one by one as we're doing, let's put them together. So we have the first bit of both coordinates. That gives us 2-bit numbers, and the order of that is 0, 1, 2, 3. So I've chosen a different axis than most people who make Morton order diagrams, so this is not actually a Z. But basically, one thing to note is you'll see this is 0 star, 0 star, so all of the 0 bits go in here, or like if it starts with 0, 0. So we'll see that a little later, how that makes things nice. We go to the next bit, so we pick any x, y for the first bit, and then look through how that bit works. And basically, each of these quadrants is now ordered in this same kind of configuration. And then we do it again, and we're one level deeper. So in this case, we have 16 subsquares, and each one is ordered in this way. So from what we just did, we can actually see 2 correspondences that are very useful. And that is that you pick any node in your octree or quad tree, and all of its leaf nodes are contiguous in the representation. So let me kind of show how I mean that. So the leaves are these guys, and like we pick one of these nodes, let's pick the node 0, 1. So that's 0 star star 1 star star. So we go down a level. That's all of these ones, and basically we're going to go through these points. It's like these arrows never cross into another node, is basically another way of saying that. It's like all of these leaves happen inside of this. So if you have an octree and you're like, well, I've got a node, what is everything in there? Go to Morton sorted order, and they're all contiguous. And the other property is that if we visit our nodes in depth first order, that is actually producing Morton order. Now maybe a little caveat with that, that means we're visiting the children in our octree in this order. So we're basically, at this level, we're going 0, 1, 2, 3, and then recursively visiting the nodes in a depth first manner. So that means we visit all the children of 0 and then all the children of 1. But you can imagine how that does it, how that works. So here in this node, we go down a level, and then we go down a level, and then we look at these first 4. We go back up, we follow the arrow, we're at 0, 1, visit these. So we're just going through everything in Morton order. So both of these two properties let you design how you deal with like leaf nodes that are for a like child voxel or leaf voxel, and group things in a way that's always contiguous, like basically a pair of indices gets you all of the points. And correspondingly, if you have things in Morton order, getting to the octree is easy because you know it's, if you just walk through the points, you're going to hit it in a way that's equivalent to this depth first traversal. So let's apply this to a point cloud. It's pretty simple. We need to define the outermost box. So we pick the root node's box. It needs to include all the particles or all the points. And then we need to decide how deep the tree goes. Once you pick that, every point will correspond to a particular Morton index. And it's a simple mapping, so you can sort all your points, and then you can build up your octree, and you're off to the races. But what did we have to do that? Well, first, for the first one, to pick the root node, we kind of need to know the bounding box of the points, right? That kind of sucks. It's like we need to go through all the points and find that before we can start really doing our work. And also, how do we decide how deep it should be? It's like, well, that's kind of related to the spatial properties. It's like if you want to be adaptive, it's like there's more points. You kind of want to go deeper there. It's like, but not here. Like, how do you pick what that bottom of the thing should be? And the big thing is that's what the spatial data structure was here to begin with. So why do we have to know this information before we're building our actually getting to the spatial data structure? So what do we need, or what could we do to alleviate that? If we made an octree that just covered all the floating point numbers, well, that would help, right? Then there's no question of what the root node is. And we can do that, and then just throw away, you'll get a chain that goes to the root that contains everything. That turns out not to be too bad. What about knowing the spatial properties? Well, we can just have that octree continue all the way down to the bottom of floating point representation. And from there, we can group things up to like make aggregate chunks and do faster processing. That's also not too bad. And the way to do this is with basically extending Morton order to work on floating point numbers. So I'm going to give you two ways to think about this. First is with fixed point numbers. And so a fixed point number is like basically an integer where you then pick where the decimal point is. So in a binary representation, you might pick, okay, 16 bits go to the integer part, and then 16 bits go to the decimal part. And it's maybe a little tricky to imagine at first if you're not used to this kind of thing, but 32-bit floats are actually all a subset of 276-bit fixed point numbers. So if we apply this integer Morton order operation to 276-bit integers, then we've got a Morton order, and that just goes naturally to the floating point. No problem. That's kind of like, that doesn't help you compute it. You don't want to like actually make 276-bit numbers for this. So I'll take this from another angle. Let's define real Morton order. So we go the other way, like all real numbers. Can we order them in this Morton fashion? And yes, we can. So any real number, you can represent it as basically an infinite sequence of bits. And you just take those, you interleave them. And if you think about how you might compare two floating point numbers made of an infinite sequence of bits, well, it's going to be that you find the first bit that's different, and that determines the ordering. And that's actually where that works just fine in this. You interleave the bits and you get the right properties, it works. Now, it's maybe a little tricky, but it works out actually quite nicely in floating point representation as well. So we had this correspondence with an octree before, the integer coordinates, integer octree. So what does the octree for this real Morton order look like? It's basically, you get a root node that's infinite, that's covering all of real space. Then it has 8 infinite children that are like the 8 octants of your real space, and 8 octants in the 3D case, actually. Then each of those octants has an infinite octree below it that is made of finite nodes. And each of those nodes corresponds to a voxel that's like a power of 2 width. Its sizes, its corners are at coordinates divisible by that power of 2. So it's theoretically it works out pretty simply. There's some special cases at the top of these 2 levels of infinite nodes, but it's pretty straightforward otherwise. And going to the floating point octree is just truncating that to the representable numbers in floating point. And the floating point Morton order is just truncating that real Morton order to floating point numbers as well. So I'll show you some code that does this. It's basically one of the ways I explained to do the comparison is finding the first bit that's different on each of the x and y coordinates, or x, y, z coordinates. And then if there's a tie for the earliest bit, taking the one that's the earliest coordinate. So first we have a function that will compute, well, what's the bit that's different? And so just using a couple of standard library functions to basically pull apart the floating point number, grab its exponent, use some knowledge of the double precision exponent of 53, or the size of the mantissa in that case, and we can say where is the bit that differs. Then we can use that to build up the full Morton comparison. It's basically go through the coordinates. In this case, I've written this code so it's arbitrarily dimensional. D is the number of dimensions in this case. And we loop through the dimensions. We find the bit that's different. If we're if the bit is sooner for this coordinate, then we override it. Otherwise, if it's a tie, we leave it. Or if it's worse, we leave it. And then we compare those numbers for that dimension. In practice, what we've done is written some SIMD code with SSE2 to sort of try to tweak the performance of this. And it works out pretty well. You get pretty good performance on this primitive operation. So that doesn't quite get us to where we need, because now we have an octree where each point in the point cloud is a leaf node, which is kind of crazy. We want leaf nodes that are a little bit chunky. They've got a little bit of data to them so that we can do vectorized operations at once on it. So we want to build up the octree and merge these nodes as we go. So the rough algorithm is to basically maintain a stack of all the node references that we've seen so far. And when we hit a point that's in a new node, we basically go through where the parent voxels would be until we hit one that's a common parent that was already seen, and then go back down and build the octree. So it's pretty straightforward to just walk through the points in floating point Morton order and build the octree. And it actually works out really nice because you're allocating the nodes in the order of a depth first search. So it's cache friendly in many ways. It works out quite well. So the final algorithm is you have your input points coming from somewhere, and you stream them directly into the sorting algorithm. So if it's out of core, it's like you'll be streaming them into something that makes sorted chunks and then does an external merge on that. If it's all in memory, it's like, well, you fill it, you sort it. You don't need to do one pass and then a second pass. It's just like goes straight into that phase of the algorithm. Then you want to go through the sorted points and chunk them up. If you're like picky about the implementation details, well, you probably want that final sorting result of your out-of-core algorithm to end up going directly to the chunking algorithm, not like write it out, sort it, and then go through it again. So, I mean, you don't have to be wasteful here. And then if when you're saving it to disk, you also say what voxel it came with. And that basically gives you a spatial format on disk that you can easily load into an octree and load anywhere in space pretty quickly. So there's one more detail that we do that is important, is that we also then go and decimate the points based on some kind of level of detail criteria. So I'm not going to go into that in depth, but let's talk a little bit about what our result is. So this is a screenshot of Sequoia. And basically, we've got a viewport, so you can see like information about the points you've loaded, and some niceties for just dealing with point clouds. And what we've been doing to test out stuff like this algorithm is like, how do we push scalability? One way to scale is towards large point clouds. We pushed it out to about 19 billion or so points. I mean, at that level, I mean, we can keep pushing it, but it's a pretty good benchmark of like how well do we work. And then the other way is pushing it towards small hardware. So we run demos on Surface tablets, and so if you're dealing with like 150 million points on a Surface tablet to like go around and stuff, that's pretty cool. I mean, it's a small device, but it can still push, like it can still handle these large point clouds and let you do stuff in a kind of compact form. This is, of course, only a small part of how you build a robust point cloud system. So we've also got a lot of asynchronous processing. So like you can keep interacting while stuff goes on, caching, multi-threading, lots of things go into it. A direction we're working more and more towards is increasing out-of-core processing and getting distributed computing into it. And this is kind of a common theme that I've seen here, like S-frame and S-array. It's about out-of-core algorithms on data frames. Dask is a library, out-of-core processing. It's a very, like there's several different angles that it's happening within the Python data community. So in point cloud software, that sort of splitting has to be some kind of spatial criteria generally. And so we're working on our different algorithms to sort of like make them work nicely in that. So the screenshot here is of Deadline, which is our render farm management system, and we're basically integrating with that to improve its ability to do distributed computing style things and mix it up with our Sequoia processing. So I'm going to finish up talking just a little bit about how does this connect to open source. So the Dyn library is a project I've started that is like NumPy, but is kind of a pure C++ library. Lets you define dynamic typed arrays, and it has some goals of connecting that kind of data between languages, like software languages, and between, in this case, between like commercial and open source software, commercial, other software, various open source software. I think the kind of data that you have in a point cloud system should be easily accessible to other systems. And the development of Dyn is sort of aiming towards being able to provide that kind of infrastructure. So that's everything I prepared. So thanks for coming, and I'll invite any questions people might have.
What kind of device do you normally collect data with? Your users collect data with?
Well, there's a lot of brands of LiDAR scanners, and that's the typical thing. If you're not familiar with what it's like, it's basically, so there's ones that you put on a tripod, and it's got a spinning mirror and a laser that bounces off of it, and it measures the time of flight back and forth. And then it usually has a camera that also takes images that it can reproject because it knows like the relationship between the camera and the laser point. So you can also mount these devices on planes or helicopters or drones and like fly them around and get aerial scans.
Are the data sets usually about 18 billion points?
No, that's a pretty, so that one, let's see, I think that was about 800 square kilometers of like the central California coast, that particular data set. The more typical sizes I've been seeing is like hundreds of millions for like scanning a work site or something. I mean, it really depends on how much surface area you're covering and how much precision you get and how many samples you try to get to cover the area.
Do you happen to have a demo on your laptop or something like that?
I do have, let's see. So I haven't prepared anything like for this, but I can maybe load up a point cloud and show a little bit of what it looks like. So here's the. Actually, wait. I've got to switch to this. Duplicate. All right. So yeah, here's our application. I'll create a point loader, and maybe. Okay, I did one before. Let's see. Yeah. Where was it? Okay. Well, so this is like a point cloud from. So it's like one piece from an aerial scan. That's just 7 million points. So the full, in that directory, there were about 2,000 individual files, and we can merge them all together in the spatial format. I didn't think ahead to do that and put it on my laptop. It's like it's on our servers back at home. If I load, let's see. So like this is so I've got this in manual mode, but, and yeah, I'm on battery on my laptop right now, so it's like in power saving modes, but kind of gives you an idea of, this is a 26 million point file, and like it's fairly interactive to manipulate. And
And who would be the most frequent customer for this kind of technology? Movie industry, game industry?
no, that it's well, the market sector is often called AEC, architects, engineers, construction. So like sites like this, where you want to do measurements on like where things actually are as opposed to where the blueprint said, or like I've heard during construction nowadays, it's like it might be cheaper to just do LiDAR scans repeatedly and see the progress of construction that way as opposed to trying to like combine the paperwork from everything getting done.
Do you have some sort of a commodity hardware scanner? For instance, if you want to scan something small, like let's say a room, is there some sort of a commodity scanner for that? And by a commodity scanner, I'm talking about, can you scan something with, let's say, an iPhone or a Kinect or something, some sort of a device where you can buy it for like not very expensive?
Yeah, well, the Kinect is exactly, I mean, any kind of depth camera technology is basically giving you this. So you, like combining like Kinect scanning with like tracking either sort of like some kind of SLAM mapping to figure it out, or like sensors on it, on the device, you can do that. Like people, yeah, use Kinects to create point clouds like this. It's definitely possible to do that as a hobbyist, yeah.
Sorry, I apologize for coming late. Maybe ask a question which was discussed earlier, but so the ability to be able to use Morton points, does it allow you to do kind of downsampling? Like you can zoom in and zoom out, it allows you how much points to fill in and like how much time to render various pieces?
The Morton order in octree isn't the thing that lets you do that, but you kind of add another level of detail layer where you decimate the points. So we decimate the points and keep it on the same octree, so we can like select, based on the camera, which level of detail should each voxel be, and then load just those ones from disk because we have our spatial index. All right, well, thank you very much for coming, and yeah, enjoy the rest of PyData.